Okay, so this podcast is going to hit on a couple of key ideas that contribute to this big topic of calorimetry. So we're going to be filling in kind of bits of page 17 and 18 and 22. We're going to skip 19, 20, and 21, but you will have access to that material later on, but it doesn't really contribute to our lab, so we're not going to spend too much time on that. So page 17 starts by talking about this equation that has to do with calculating the amount of energy required to cause a substance to go through a phase change, meaning how much energy is it going to require to melt something or boil something, vaporize it. And it comes back to this quantity H. The heat of fusion or the heat of vaporization is a constant for different substances, and we plug that number in order to calculate how much energy is required to melt something or boil something. Now, that number can be negative or positive, like heat of fusion could be for melting or for freezing. It's the same H number, it's just positive versus negative depending on what's happening with the energy. So there's a couple of problems here that you can copy down or not. I'm not going to really ask you to do these problems. They're pretty simple though. They give you a mass, then you either look up or are given the H value, you multiply them together, find the answer. We can use it to answer some more complicated questions like what mass would be required to absorb this much heat and energy. That kind of math is involved in calculating things for like heat sinks and computers and other types of technical devices. It's everywhere, but it's pretty simple. The key idea with this calculation is to point out that with H, because it measures the amount of energy needed to cause a substance to change state, then the smaller numbers melt first or have that change happen first, and the larger the number is, the more energy it requires before it will change state, and thus it will melt last. So let's get to the actual calculations we're going to need, and it's related to this 3-minute shake idea. And you can see the equation we're going to be using up there in the corner, but really the big idea that you would get from this when we shake two different materials in two different in the same kind of container for the same amount of time, they're going to heat up because you're adding energy to them, but one of them will get hotter based on this idea of specific heat capacity. This C here in this equation is a lot like the H in that last equation. This is just the energy needed to make something change temperature instead of change phase. So a low specific heat capacity, a low C, is going to get a large change in temperature. And almost forgot to mention that this C as well as that H is an intensive property, meaning it's constant no matter how much of a substance you have, and that makes it really useful for identifying substances by. But back to our specific heat capacity changes, just like we saw with the H, the larger numbers mean that they're going to require more energy before they change. So bigger specific heats have small change in temperature if everything else is equal. Now, a number you're going to be using a lot is the specific heat for water. 4.184 joules of energy is required to change 1 gram of water by 1 degree Celsius. And there are a lot more C's that we're going to be using. They're on the page 21 and 22 charts, and we'll be kind of flipping by those as we get to page 22 in just a bit. But there's a couple of questions here on this page we're going to answer first. First, taking a moment to define what each of these variables is in the equation. Pretty much predictable. I know it's a little weird that heat is Q, but I think they just kind of started running out of letters by the end of the course. And M is, of course, mass. C is our specific heat. Delta T is our change in temperature. So it's not just one temperature or the other. And we do calculate delta T by taking the final temperature minus the initial temperature. Really, we're going to talk about that when it comes into play a little bit more and see that we can kind of reason our way through that definition and the signs that are going to be on these problems. All right, so with this problem that we're looking at, we're trying to calculate the heat required. So that's going to be our Q that we're looking for to warm up something with a mass of 750 grams of water. And that water tells me what my specific heat should be, since liquid water is always 4.184. And if my temperature is changing from 10 degrees Celsius to 80 degrees Celsius, final minus initial, means that my temperature change is 70 degrees Celsius. So plugging all of those numbers in. And so the Q that we should be getting in our calculator is 2196.6, which if we round this to 3 significant figures would be 2200, but we'd be trying to keep only one of those zeros significant, which we can do by drawing a line, but that's kind of weird and hard. So the best way to write this answer out with 3 significant figures would be scientific notation. So 2.20E3, and no matter how we write our final answer out, that should be joules on our answer. All right, so now in this question, it gives us the heat that's being released, so I am writing that out as a negative number, and then it gives us our mass, and we're trying to figure out what the specific heat is, so C is going to stay in our equation, and then if we subtract our two temperatures, final minus initial, 35 minus 42 gets us -7. So that's going to kind of balance out or kind of cancel out the negative on our heat that we put in there, so that our specific heat is just a positive number basically, but we'll get to that in the algebra portion of this. Now that we've found all of our numbers, we can start simplifying each side, and of course this side with the heat's pretty simplified already, just combining the -7 and the 10 into -70. And then we have to divide by -70 so that it'll cancel out on this side. And when we do that division, our C ends up being 0.291. And I did find that barium evidently has a specific heat around that point. But I would have to do some further research in order to use this number to identify our unknown substance, probably use some other, physical properties, chemical properties of it in order to identify it as well. But we are well on our way because this is intensive. This can help us identify our substances. So we've got one more calculation here. It's a little bit different than the ones we've done, but still just pay attention. We're looking for the mass here. Find all the numbers. I've given you a little hint here about our specific heat to help get you going, and then you can finish that out. So we're going to keep going on to page 22. And actually, before we get into it and start writing down a lot of notes, I just want you to think about this idea. I put hot metal into cold water. What's going to happen? Hopefully, you're telling yourself that the water, which was cold before it got the hot water in it, is going to get warmer, and that hot metal is going to get colder, because that is, in fact, what happens. They're going to come to what we call an equilibrium point in between them, where their equal energies are going to stop transferring heat to one another. Even if that temperature doesn't change by the same amount, you see here the cold water's arrow is just a little smaller than the hot metals, then the total amount of energy transferred is going to be the same, because all of the energy, the heat from that hot metal, is going into the cold water. So the heat transfer is the same, even though the temperatures are going to be different. And we saw how having different specific heats for different materials with these previous equations we've seen could cause those temperatures to be different while having the energy be the same. So you have written down in your packet this idea of heat lost equals heat gained on page 22 at the top. We're going to expound on that just a little bit to get kind of the usable equation, the usable version of this. So wait a second before you write anything down. When you're saying heat lost equals heat gained here, okay, so heat is really represented by Q in all these equations we've been working with. So Q lost equals Q gained. And really, in calorimetry, we're dropping some piece of metal or some substance like a metal into water. So the heat lost by the water is being gained by the metal, or vice versa, depending on which one is warmer. So because these things are changing temperature, the Q equation we're going to be using is the Q equals mc delta T. And if we plug that in for both of our Q's on both sides of that equation, this gets to be a little bit big, but this is actually kind of our calorimetry equation that we're going to be using here, setting the mc and delta T of the metal and the water, respectively, equal to each other. We can solve for any of these variables that are unknown. So in these next two problems that you see down below, I'm going to have this list of variables written off to the side because these are all the numbers we're going to be looking for. It might seem like a lot, but kind of like the last couple of equations and calculations that we've just been doing, after we plug the numbers in, we're just going to simplify either side of the equation and then solve for whatever we don't have. So let's go ahead and look at a problem. You'll see these two tables of specific heats here that we're going to be using on this page, and we're going to need to come back and look at these probably as we're working in the rest of the packet problems as well. So the first problem, and actually the only problem I'm doing with you, tells us that we have this 55 gram sample of a metal at 90 degrees Celsius. That's our metal information. Dropped into a container of 250 grams of water at 22 degrees Celsius. That information is all about the water. Then it tells us the final temperature of that system. The water and the metal end up at 23.4 degrees Celsius. And then it wants us to use this information to identify the metal. So that means we're going to be looking for the specific heat of the metal, kind of like that last problem that we did. Finding specific heat helps us identify the metal. So plugging those masses in here, we always know that specific heat of water is 4.184. Now we need to do some subtraction. Now before I was making sure to do final minus initial with these so that we could make sure that our delta T's and our heats canceled out, but technically what we're doing here, setting these equal instead of equal and opposite, is a little bit off. So let's just make sure that our numbers turn out positive, because all of the numbers that we plug into here should really be positive as well. So we're going to take the bigger temperature minus the smaller for each of our substances here and find how much, just the degree to which they change temperature. We know that they are changing in opposite directions, but introducing negatives here is just going to cause more headaches, not less. So we've done our background work, found all of our numbers for each of our substances. So next step is to plug them in. The only thing that should be left over and not have a number is that C on the metal side of things. I've called that CM. And then if we consolidate all our numbers, so multiplying together our 55 and 66 here to get this 3663, and then multiplying all three of these red numbers together to get that value, our next step would, of course, be to divide by the number on the side with the variable we're looking for. So we're dividing by 3663. And when we do that division, then our C ends up being 0.3998. And if we go back and look at the specific heat charts, then that seems to be pretty close to copper. So evidently this metal is copper, and hopefully it looks kind of coppery too. That's a pretty good diagnostic in and of itself. So that's really all we're doing here. The math isn't that hard. You just need to make sure all the numbers go in the right place. So I've color-coded this next problem just to make sure that you're getting these numbers in the right places. Gave you that C for water again because it's always the same. Go through this same process that I just did with the last one. Find that specific heat of the metal and use it to identify what you've got there. If you have time, we'll have a little bit of time in class, then you could start working on some of these Q equals MC delta T problems on that last page of your packet. Those are the only ones I want you to practice because those are the only ones we're really using for calorimetry, which is the whole point of these calculations for us. You will need some C's from page 21 and 22, so I've gone ahead and written those here. If you want to copy them down, that way you won't have to be flipping back and forth. So that's it for this podcast. Hopefully it makes sense. Let me know if it doesn't. I always want to help.